So we talked about the trade-off between order costs and holding costs. And if you add the holding cost and order cost together, you will get the total cost. And you can see from this graph that if you add 2 points on this green and blue lines, it will add up to red. Let me just show you one example. So for example, the order quantity at this point, if I go vertical line, will be right here is going to be my holding cost. If I keep drawing my vertical line, I will get the ordering cost associated with that order quantity, let's say 1. And you will see here order cost 1 and the holding cost 1. So if I add holding cost 1 and ordering cost 1, that would give me the total cost 1, right? So if you add up again blue and green lines together, you will get the red line. Another example would be, let's say, order quantity Q would give me right here the same amount of order cost and holding cost, and that will be right here the total cost 2. And this is my holding cost 2 and order cost 2. So the lowest point of total cost here is where these two functions intersect. And to understand this intuition a little better, so what would happen if I had my order cost not like this, and if I had it more like this kind of line, linear line, then basically that would flatten my total cost to something like this, right? The total cost would push up. It would be higher because, as you see, this dotted green line right here is greater than this solid green line. So that ball shape of this red total cost would flatten out. What if I had my total cost not like that, but it's more like this kind of linear line? And of course, then my linear line would drop my total cost. So my total cost would more like look like again flat, but more like this kind of flat total cost line. So the shape of these lines, of course, impact the red line total cost. And since this is again convex function here going downwards, that would give me the total cost that's lower right here. Okay, so if you really want to find that, what you could do is actually add 2 lines. It's out of scope of this class really, but I know my ordering cost and holding cost functions. So if I add them up and then take the derivative, then I could find the lowest point right here. Okay, so it's a convex function. Again, total cost is a convex function. Total cost is holding cost plus ordering cost. And really, if I took the derivative of this on order quantity Q, then basically I could find this lowest point. But again, this is not in scope of this class. So let's talk about the minimizing the cost. We have here Q, which is number of units per order. Q star is the best value of Q. And D is the annual demand, S is the setup or ordering cost, and H is the holding or carrying cost. So again, S and H, these are 1, 2 cost components, right? So how would I calculate my annual setup or ordering cost? It is quite simple. I could multiply number of orders per year times, I could multiply this value by order cost per order. Okay. So how would I calculate number of orders per year? Basically, annual demand, which is D, over number of units ordered, which is Q. D over Q will give me that value. If I give an example here, say if I'm ordering every time 100 units, and if my yearly demand is 1,000 units, 1,000 over 100, which means 10. That means that every year I need to order 10 times to be able to have my demand satisfied, which is 1,000. That's why D over Q, 1,000 over 100, times my order cost, which is S. Let's say if I spend every time I order $100, basically I need to multiply this D over Q number of orders by S. That would give me my annual ordering cost. How would I calculate the annual holding cost instead of ordering cost? So that's also quite simple. So I need to first figure out what's my average inventory. Average inventory. And this is quite easy because my average inventory, if you look at this graph right here, this right here, which is in the middle of Q and 0. Middle of Q and 0, since it's a linear line, is Q over 2. This is Q over 2. Times, I need to multiply that value by holding cost per year, which is H. That would give me my holding cost, annual holding cost. So we graphically show how to calculate the lowest total cost. We say that the lowest total cost is where ordering cost and the holding costs are equal. Okay, so if I plug in these two formulas right here, D over QS is equal to Q over 2H. Then if I put this Q over here, then I will get 2DS over Q is equal to QH. If I put this Q over here and this H on the left, and then if I carry Q to the right, what happens is that 2ds over H will be Q squared. If I take the square root of both sides, I will get Q is square root of 2ds over H. Okay, so that's the formula, and that's the optimal order quantity where it will minimize total cost. So let's do an example. So annual demand is given, ordering cost per order is given, holding cost per year per unit is given. So I can calculate my Q star, which is square root of 2 times 1,000 times S, which is 10, divided by H, which is 0.5. So 2,000, 20,000 divided by 0.5, 40,000. So square root of 40,000 will give me 200 units. So every time I order, I should order 200 units to minimize my total cost. All right, so then let's try to figure out expected number of orders per year. All right, that's simple too, and is denoted as expected number of orders. So basically, I need to divide demand, annual demand, by order quantity. Order quantity. Okay, so my D is 1,000. If I divide 1,000 units every year, and I order every time 200 units, Q or Q star in this optimal order quantity, that will give me 5 times. So I need to give 5 orders per year. Another question is, what's the expected time between orders, T? So I order 5 times, that's what we calculate here per year. Then we need to figure out number of days, working days in a year. Let's say we work 250 days in a year, and I have 5 orders per year. 250 over 5 will give me 50 days. That means that every 50 working days, I need to order a new batch. So another question could be, what is the total annual cost? Again, annual cost is setup cost plus holding cost. So I know that the setup cost formula, we say number of orders, which is D over Q, times ordering cost S, plus average inventory, which is Q over 2, times H, holding cost per year. So if I plug in my values here, 1,000 divided by 200 times $10 plus 200 order quantity divided by 2 times 0.5, which is 50 cents. That would give me $50 plus $50, $100. So that's the total cost, which is the minimum cost for this problem. So in EOQ model, actually we could also include the actual cost of material, which is going to be denoted by P. Then my total cost function will change, setup cost plus holding cost plus product cost extra. So we know that again, setup cost is D over Q, number of orders, times S, order cost per order, plus average inventory, which is Q over 2, times holding cost per year, plus now I have product cost per product is P, times I have annual demand of D, so that would give me my new total cost. How about reorder point? When should I order more? So EOQ answers the how much question. The reorder point tells me when should I reorder, right? And it depends on the lead time. And lead time is the time between placing and receiving an order. Right? So then reorder point is demand per day times lead time for a new order. Lead time for a new order in days, right? So for example, if you are gonna order again toilet paper, and if you use one toilet paper per day, and if it takes you 3 days to receive your toilet papers, you better choose your point something greater than 3, because it will take 3 days while you are waiting for your toilet papers to arrive. You will keep consuming it. So if you don't want to run out of toilet paper, you better calculate your reorder point based on your daily demand times lead time, right? And if you don't know the small d here, you can calculate small d by capital D, which is annual demand, divided by number of working days, right? So let's look at a reorder point on a graph. As you see here, this is my reorder point, and this is my lead time right here. So I need to order my products here because I know that it will take this many days, L number of days, until I get my products back again to me. So I need to cover, really, I need to have enough inventory for L days, right? Otherwise, I will be out of inventory. Again, this is right here, or the same thing right here. This is the stock replenishment. And the slope here is your demand, right? Those are important things. The more demand per day you have, the faster this red line will go down, or in other words, the slope will be higher. All right, so reorder point example. So let's take a look at this example. Imagine that I have the annual demand of 8,000 iPhones, and I have 250 working days here. The lead time is 3 days, may take 4 days. So I would like to calculate my reorder point for both scenarios, all right? So my reorder point then is D times L. So I don't know the demand per day. I know demand per year. So to find demand per day, I can divide capital D, which is demand per year, by number of working days, which is 250, times I can multiply by lead time of 3. That would give me 96 units. If I use the lead time of 4, then that would give me order point 4, lead time of 4. Then that would be times 4 is of 3, and I would get 128 units. So whenever I reach 196 or 128 units, I need to reorder. An extension of EOQ model is production order quantity. Instead of buying those products, now I'm producing in-house. So the difference here is really there is a slope here. As you see, while my inventory is replenished, there is a slope. It's not a vertical line. The reason is that while I need to produce, first of all, to be able to build an inventory. And while I'm building an inventory, I continue to sell my products. So right here, this is small t right here is the time where I produce my products, right? So this is your inventory during production. So I produce here, and then at this point right here at time t, I stop producing and switch to another maybe type of product to produce. So now I only sell those products, and my inventory levels, as you see, going down and down. So this is your demand right here without production. Without production. And this is your maximum inventory level right here. And I will keep repeating this cycle over and over again. So in this case, really, if I have the batch size of Q, I can never reach this number is less than Q. The reason is that while I'm producing the batch size of Q, at the same time, I have demand that I need to satisfy. So I can never really reach to Q because it's something smaller than that. So let's look at again the holding cost and order this time, not ordering cost, setup cost this time. Let's look at first holding cost. So annual holding cost is very similar to EOQ model. So you need to find your average inventory times holding cost per unit per year. All right. So I have this holding cost H per unit per year given to me right here, but I need to really understand what's my average inventory. And again, average inventory is right in the middle of this, right? This is gonna be my average inventory. But the problem is that, again, the highest point of this hill is something less than Q. I don't know exactly what it is. So now I need to figure out my average inventory, okay? So basically, I can find that average inventory by this one right here. So average inventory is nothing more than maximum inventory divided by 2. The reason is that, again, this is a linear line right here. This is a linear line too. So this average point is, this is 0. This is something less than Q. The average is between the peak point and 0, right? So right in the middle. So now I need to figure out the maximum inventory that I can reach. So how many can I reach? So as you see here, I'm producing for T time and assuming that I produce P units per day. That means that in T number of days, I can produce P times T, because I produce P number of units per day and I produce for 10 days. Like for example, if the T is 10 days, and if I can produce, let's say, 10 products per day, that means that in this T time frame right here, I can produce 10 times 10, 100 units. But in the same time, I have demand. Let's assume that my demand is, let's say, 5 products per day. Then, literally, in this T production time frame, I consume small d times T. In this case, 5 times 10, 50 units. So what's remaining? I produce 100 in 5 days. In 10 days, sorry, and I consumed or sold 50 units, so remaining is 50. That's why PT minus DT is gonna give you your maximum inventory level. So if I plug in this over here, that would help me to calculate my average inventory. So if you do that, you will get maximum inventory level, which is right here. So I can calculate the I can calculate really the average inventory. So let's go step by step here. If I plug in this one here, my average inventory is nothing more than PT minus DT, which is maximum inventory, divided by 2. If I plug this one over here, I can calculate my holding cost. So annual holding cost is nothing more than PT minus DT over 2 times the holding cost rate per year, H, right? So that would give me my annual holding cost, all right? So what's happening here? All right, so I would like to simplify this equation a little bit. We say that this maximum inventory level is PT minus DT. However, the total produced is not the same thing. So in this T time frame, I produce really P times T units. In the example I gave you, if I produce 10 per day, in 10 days I can produce 100 products. Thus, if I put this T, if I want to figure out T, how many days could it take me to produce Q number of units based on the P production rate, then that means that really T is equal to Q over P. In other words, if I want to, let's say, batch size of, if I have batch size of 100 units, if I want to produce 100 units, and every day if I'm producing 10 units, then it will take me really 10 days to produce it. That's what we talked about, right? All right, so what I'm gonna do is now maximum inventory level was PT minus DT. Instead of using that formula now, what I'm gonna do is I will replace all the T's with Q over P. So if I do that, P times Q over P, right? P times Q over P, I just replace this T with my Q over P, is the same thing, right? Minus D times Q over P. All right, very nice. So that means that really this P and this P is gone. So if I put this in Q parentheses, both sides of this negation or a minus sign, I will get Q times 1 minus, right, D over P. That's the same thing. Q times 1 minus D over P. All right, so now I can plug this one into my holding cost calculation, right? Holding cost is nothing more than my maximum inventory divided by 2, which is average inventory. If I divide Q over 2 times 1 minus d over p, right? Because divide by 2 because